Okay, so let's start the class. Do remember that you need to study from the textbook, okay? It's not required that you get the last edition, but it is required that you study from the textbook. So it's going to be Kinematics 1D. And then make sure you study before the class, you have your class, you study after the class. So it makes the digestion easier, right? It's the little spoon of sugar that let them go down, you know? So every class that you take, it's always easier if you read the textbook before, even if you don't fully understand what's going on. Then you have your lecture, and then you go over the textbook again. So for the textbook, it's very important that you hide the solutions of the solved problem and you try to do it on your own. For the assignment, you have to do the first trial on your own or with your group study before picking at the solution, which is in Dropbox. And then I add here and there a few challenging problems, kind of. Since you're stuck with me for one semester, it will be great if you get most of it, especially if you want to be engineers, you want to have a solid foundation. So if you want to take the MCAT or the GRE or whatever. Okay, so I think we stopped here. And I want to use graphs to introduce the kinematics equation. Very important to use graphs to have all your ideas. Okay, so let's take a first example. Let's see, initial position is going to be 0. And then velocity, I'm going to take that to 5. Now it's stuck. 5 and no acceleration. So it means when you start your stopwatch, initial position is 0, but it was already moving at a speed of 5 meters per second. So the velocity is 5, which means it's moving to the right. Okay? So let's see what we get. So it's moving at a constant speed. So every second, the car is covering 5 meters, right? So let's look. So this is a very simple case, but let's look here at the equation that we have just using algebra scale. So here you can see the acceleration is 0, right? Acceleration is 0. You have a horizontal line, so that means it's a constant value. The velocity is plus 5 meters per second, right? So the slope here is 0. Okay, so the value is constant, the slope is 0. And remember, the acceleration is the derivative of the velocity. If you take the derivative of a constant, you're going to get 0. And then you get to the position. Okay, you see that every step in 1, you go up by 5. Or you can say every step of 2, you go up by 10. Okay, so the slope is a rise of 10 and a run of 2. 5. Do you all agree? Remember algebra? Right? So it's a linear equation, and we're going to write x equals, what's going to be the slope? 5t. Okay? So look at the unit, meter per second. So typical conceptual equation, the slope of a graph, position versus time, is the velocity. And the velocity is constant and positive. So the slope here is plus 5 meters per second. So that's what we call a kinematics equation. So to understand the graph, it means that every second, every second you cover 5. 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 So the number line is here, which means you start here. After 1 second, you're going to be here. Another second, you're going to be here. Another second, you're going to be here, 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 here. So it's the same thing, except you unpack. You have the time here. Okay? Yes. So the velocity is the slope. So slope is rise over run, and rise will be on the vertical axis. So you see it's a meter, and run is on the x-axis, which is second. So if you don't remember, you just look at the unit. Rise over run, meter per second. Position on the number line as a function of time. Okay? Okay, let's do. So you can try to do that. Initial position is 5. So in your head, you can predict what you're gonna see. So it's still when you start your stopwatch, okay, the car is already moving, except that the position will be 5. Okay, so once you start your stopwatch, the car is moving, but the position is going to be here. Agree? Okay, so let's see what we see. So it's still no acceleration. The velocity is constant, but the initial position is 5. So the graph has been shifted up by 5. Okay? So that's also easy. Okay, just to connect with basic algebra. So acceleration is 0, velocity is 5 meters per second. But now, when you start your stopwatch, okay, so it was already moving, and the position here, initial position is 5. I should have put 10, but it's fine. 5. So that's when you start your stopwatch. Okay? So what's the equation? X as a function of t, it's going to be 5. Very good. The y-intercept, you all agree? Okay, 4 plus 5t. If you take the derivative, okay, what you get? 5. And that's the definition of the velocity. Sometimes if they can calculus, they call that x dot. Okay? If you derive a second time, okay, so if you derive a second time, you're going to get the acceleration, which is derivative of a constant is going to be 0. And sometimes this is called dot dot, just to look smart and to confuse students. Okay, so let's see now what we're going to have if we have an acceleration. So I'm going to take initial velocity is 5. Let's take initial position is 0. But now I have an acceleration of 1. Okay? Can you think in your head what you expect for the acceleration, which means the rate at which the velocity is changing, how fast you are going faster, and what should you expect for the position? Parabola for the position. What about for the velocity? Straight line. Do you all agree? Let's see. So it's moving faster. You see, the vector velocity is increasing. Okay, it's accelerating. Okay, so that means that if I make a dot at t equals 0 is going to be here, and then at t equals 1. So let's first do that. So acceleration is 1. What does it mean? It means for every step of 1, your speed will increase by 1, right? So it starts at 5. After 1 second, it's going to be 6. After another second, it will be 7, right? So the slope, every step of 1, it goes up by 1. So what's the equation? The velocity will be equals to whatever you begin with, which is 5, okay? So that's the y-intercept, plus, and then you have the rate. And the rate is 1 times t. So we call that invisible 1. So it will be v equals 5 plus t. Now, if you take the derivative, okay, what you get? If you take the derivative here, what's the coefficient? 1. It's an invisible 1. So the derivative will give you 1 meter per second per second. Yes, someone asked me something? Yes.
Why would we, like, how did the computer know to start time? Or why are we starting at time?
Because that's me that decide. I decide to start at 5, which means that here it was already moving. You could start at 0 actually. You can make it start at 0 and then it will accelerate. So here I start at 5. Okay? So for example, I could decide that initial velocity is 0. I can reset. And now I can say initial velocity is 0. So what does it mean? It means when you start your stopwatch, you have a stopwatch in your hand. When you start your stopwatch, how fast it was moving. You don't have to start at 0. You start your stopwatch whenever you want. So I can start here. And in that case, you see there is no y-intercept. So v equals 1 times t. Okay? So in that case, it's a parabola. Okay? So you see that I should have put initial velocity equals 0. I will show you the difference. But you see that at t equals 0, you have a slope. And what is that slope? Position versus time, it's going to be the velocity, right? Because rise is meter, run is second. And what's happening to the slope? It's increasing. Okay, it's getting steeper and steeper and steeper. But it increases at a constant rate. So if you take the slope, which is the tangent, okay, tangent the angle, that slope for every run of 1 second is going to change by the same amount. That's how we define a parabola. So how we define the equation? So we know it's going to be a parabola, so it's a quadratic equation. And we're going to see that it's going to be x equals, so first we need the initial position. Initial position is 0, very good. So 0 plus, and then I have to take into account that to begin with, I have an initial velocity. So it's going to be v sub 0 is what? T, 5 t plus 0.5 times the acceleration times t squared. Okay, it's just an introduction. I will talk about that, but you can see that it's a parabola because every second it's going to move faster. Right? So it's going to be here, then it's going to be here, and then it's going to be here. I will give you more examples just to get a gut feeling of what is going on. So you expect a parabola, and you expect a what is called quadratic equation. Yes.
Which is 0.5.
From the quadratic equation. So it's like that. It's a definition. I will. No, actually, you are right. I'm going to explain. You can do it this way. Okay, it's a good question. V equals 5 plus t. Do you agree with that? Okay, to get the position, you need to integrate. Okay, because velocity equals dx over dt. So you can have delta x equals the integral between time, let's say indefinite integral, and then here it's going to be v dt, right? So you take the integral. So if you take the integral, what do you get? V equals what you have here. 5t, very good, plus 1/2 t squared plus c, you're right. So at t equals 0, that will be your initial velocity. And so c will be the initial, no, that's x, right? So that will be, c will be the initial position, right? So that's how we get this equation. Don't panic, we're going to get to that. Is that clear? But it's a good question, so you can connect to calculus. So to go from here to there, you take the integral, and then to go from here to there, you take the integral. And how do you undo an integral? You derive. So from here to there, you derive. From here to there, you derive. Okay? So I went a little bit fast because I should have taken this example here where you do not have initial velocity, which means when you start your stopwatch, the car is not moving and you hit the gas. Okay, so in that case, so here, what's the acceleration? 1. So what does it mean? It's moving 1 meter per second faster every second. So every run of 1, it's going to move faster by 1. So the equation here is just v equals, the slope is 1. So v equals t. It's supposed to be a nice diagonal. Not sure, but that's it's supposed to be. What about this parabola here? You see at t equals 0, does it have a slope? No. So that means initial velocity is 0. And the slope, the tangent, the steepness, because you remember, a slope, what is a slope? A slope is the steepness, right? Is the tangent. So if you say 10% slope, that means like if you go on the treadmill, I try to do 15%. So 15%, what does it mean? That means 15 here, 100 there. So it's the same thing. It's like a treadmill. So every step of 1, you increase by the same amount. Agree? Okay. So x equals, if you integrate,
1/2 t squared.
very good. And that will be the equation of your integral. Okay, so we are looking at physics with math glasses. So maybe it's easier this way. Okay, so then what else do I have? What about if I put an initial position here? What's going to change? So it will be the start position that will change. You agree? Is this going to change? No, very good. Is it going to change? No. Is it going to change? Yes, right? So it's a shift, a vertical shift. Okay, you take your graph and you shift it vertically up. So let's see. You see, you still have your parabola. Okay, no problem. And you still have your initial velocity to be 0. Okay, so if you understand and if you use up it's easier to digest physics, because if you memorize, it's not very helpful. So A equals 1, V equals T, very good. So X, the position, equals the y-intercept 10 plus, initial velocity is 0, so 0.5 t square. Is that right? Okay. So that's how it works. Okay, another example. If so, you can play with it. Okay, so initial velocity is 5, for example. What's going to change? Is it going to change here? No. Is it going to change there? Yes, because you expect to have a y-intercept of 5, right? And here, the slope that you begin with will also change. So we are not really doing physics here, right? We are just doing math. If you have any question, not everyone has the same background. So if you are too shy to ask, you can see me after. Okay? So A equals 1, V equals 5 plus T, very good. So 5 is the y-intercept. X equals, what's the initial position? 10 plus 5t plus 0.5t squared. Is that clear? You can take the integral and you will find that. So that's why math is essential, of course. By the way, do remember that the one who invented calculus is Newton. Hmm?
And Archimedes.
And who?
Archimedes.
Archimedes invented calculus?
Integral.
Oh, really?
Yeah.
Are you sure?
Yeah.
Not geometry? Oh, I didn't know that. Interesting. I know that you have the German guy, Leibniz, also invented calculus, but it's not really clear that Leibniz maybe stole from Newton. Because Newton has some issues, right? He had a lot of issues. So he didn't publish. And if you go to graduate school, they say publish or perish. That's what they say. I don't know. Okay, so let's try to do that. So initial position should be okay. So it has an initial velocity of 10, and now the acceleration is -1. So what's going to happen? Huh? What's going to happen to the velocity? Slow down, right? It's going to slow down at a rate of 1. And here we go. Slowing down, slowing down, slowing down, slowing down. Stop. And look, if you keep, that doesn't happen in the real life, but if you keep pulling in this direction, then it's going to come back. So that's very interesting, because remember, acceleration means force. If the acceleration is to the left, that means there is a force to the left, right? So that means something is pulling to the left. So not only it's going to stop, but it's going to reverse the...
It can be also said that a negative acceleration is going reverse. For example,
Yes.
if I am driving and I put back, that is a negative acceleration, even though I accelerate.
Right? So it means because of course we imagine car, we never seen car going backward, but for example you can imagine like training at the gym, and you start to run, and maybe your coach here, right, have a coach and attach like an elastic, right, and then it's loose first, right? So you're going to start running, but you're going to slow down, slow down, slow down, slow down, slow down, stop. And what's going to happen to you? You go back in the opposite direction. It's not a good example because in that case, the force will change, right? Or as you stretch the rubber band, the force will be larger. So I don't know, maybe some kids, start to run and I grab the kid. So I keep pulling, 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 pulling. At some point, the kid is going to stop and reverse, right? And or in a spacecraft. So if you have a spacecraft here, and okay, so it's moving this way, and now you reverse you go in the retrograde engine. I mean, you're going to push this way, so the spacecraft is going to slow down, slow down, slow down, stop, and reverse. Okay, so it's a good question because the easier example is this. You see my notebook here? Okay, so is there a force acting on it? So where's the force? So it's down, right? So the acceleration is where? Down. So I'm going to throw it up. So on the way up, okay, it's going to move up, right? So the velocity is positive or negative? Positive. And the acceleration is negative. At some point, it's going to stop. So now the acceleration is still negative because the force, the weight, it doesn't stay, okay, I'm tired, pulling on you, go. No, right? You always have a weight, and then the velocity will be negative, right? So you see, slow down, stop, speed up. So here it's exactly the same situation. Yeah.
Sorry. You throwing the notebook off, would that because would you reinforce as well throwing the notebook off? So
When I throw it up, the only force acting on that object is the weight. When I do it, of course, there is a force upward when I touch it, right? But once I let go, so it's only gravity acting on it. That was your question?
yeah, the up, the acceleration be positive. That's
So when I do this, that means I'm stronger than gravity. So the acceleration will be up, right? I make it go up. But once I let go, the only force acting on it is going to be gravity. It will be the net force, right? So here the acceleration is -1. And here the velocity is positive 10, but you look at the magnitude, okay? So it could be very tricky to understand a graph. So what's happening to the magnitude here? Is decreasing. Do you see that? Decreasing, decreasing, decreasing. At that time here, what's happening to the velocity? 0. So it means the car has stopped. And look at the magnitude now. Is the magnitude increasing, decreasing after t equals 10? So it's going to increase again in magnitude, except it's negative. So what's happening? The car is slowing down, slowing down, slowing down. Stop, reverse, and speed up again. Because the force is to the left. Okay? So we'll talk about that. But here the stop is positive or negative. The slope is negative, right? So V equals, what's the y-intercept? 10 minus 1 times t. So that's the slope. Okay? So what does it mean? Every second you go 1 slower. Is that clear? And here you have a parabola down like this. So it's still a parabola. So x equals, you see, you have an initial slope. So it's going to be 10t plus 0.5 minus 1 t squared. Okay, you can just take the integral, or otherwise we will discuss all that. Is that clear?
Yeah.
So this situation is free fall. You throw something in up, it's gonna slow down, stop, and then speed up. Okay? So do not worry. We'll do that again. But it's important to understand. So initial position, I'm gonna do 50 here. Initial position velocity is gonna be 0. So imagine in your head, what do you expect for the graph? So where is it when you start your stopwatch? 50. The acceleration is negative, so there will be a force to the left. Very good. So something is pulling the car to the left. So what's going to happen to it? It's going to accelerate to the left. Very good. Because there is no initial velocity anyway. So it's just moving to the left and it's going to speed up to the left. So that will be the situation when you take an object like this, you just drop it and it's going to accelerate down. Okay? So acceleration is -1. The velocity here, y-intercept is 0. What's the slope? -1 times t, so minus t, exactly. Okay? Remember, you look at the unit. Rise is in meter per second, run is it second. So meter per second, that means that the slope is the acceleration. You look at the slope. Okay? Here, the slope at t equals 0. What's going to be the slope? 0, right? Flat is 0, and then it keep increasing. So x equals initial position is 50, slope is 0 here, okay, plus 0.5 acceleration -1 t squared. Okay, so you take a parabola, y equals x squared, you put a minus in front. So flip it, you make it wider because you multiply by 0.5 and you shift it 50 up. Those who want to connect with algebra. Okay, so that's just an introduction. So kinematics variable, you have displacement, it's a vector. Acceleration is a vector. Initial velocity, final velocity are vectors. Time is a scalar. Okay, let's do easy stuff. I don't think we did that, right? What do you think? You can talk to each other? Ideally, I should have a clicker. Some click. So click in your head. So what do you think? A, B, C, G? C? C? Okay, it's a C, right? So it means that the velocity increases by 2 meters per second every second, okay? So the acceleration here, if it increases by 2 meters per second, that means it's not a constant acceleration, it's called a jerk. That's what it called when you change, like you go really fast, when you start your car very fast. So anyway, what do you think here? Huh? Constant velocity. Okay. This one, you have to remember that if there is an acceleration, there is a force, and the force is in the same direction as the acceleration. So you want the acceleration, so the force, to be null. C, so traveling south and its speed decreases. So yes, C. Right? Do you all agree? Okay, so if something slow down, acceleration and velocity, they have opposite direction. So east and then slowing down. So the acceleration is what? West. Okay? So opposite direction. So easy. So when it says in a problem from rest, that means initial velocity is 0. That's how you translate that. So final velocity is 25, initial velocity is 0, time elapsed is 10. What's going to be the acceleration? 2.5. Do you all agree? Okay, acceleration is the change of velocity over the change in time. Which one is not a vector? Speed is not a vector, right? Average acceleration, it's like shifted. I mean this thing here, right? So it's kind of there. But anyway, that's the answer here. So I get, yeah, that will be D because it shifted. So this one goes that, then goes here. So I get it's D. So it doesn't matter. The answer is this. Okay. Okay. So here, all the solutions are in my Dropbox. But let's see. It's easy. This one is easy, right? Number 6. If you increase at a rate of 4.2 for a time of 5 seconds, what's going to be the velocity at the end? You just 4.2 by 5. Do you all agree? Because it means for every second, you go faster by 4.2. So after 1 second, 4.2, 2 seconds, 4.2 times 2, 3 seconds, 4.2 times 3, and blah, blah, and blah, blah. Okay? So number 7, the acceleration, is it positive or negative? It's negative. Do you all agree? Okay, because you decrease the velocity. Okay, here are the infamous kinematics files. Physical quantities, final velocity, initial position, final position on the number line. Delta x, important, is the displacement. It's the final position minus the initial position because you are working in 1t. A is acceleration, t is the time elapsed. If there is an acceleration or deceleration, like if you are moving faster or slower, then you want to use those equations here. So you see the position as a function of time, it's a parabola. So sometimes you can move this on the other side and you have delta x, the displacement, initial velocity times time plus 1/2 at squared. Copy me? Yeah. Okay. Yeah? Like it would be x. So here it will be x minus x1. Right? So it means you have to be careful with that. That means x, the final position. So you are on the number line. So, but maybe your initial position. That's important to understand. So initial position can be here. What does it mean? It means you start your stopwatch here. Okay. And maybe when you start your stopwatch, you do have an initial velocity. It's a very important concept here. So here, when you stop your stopwatch, the location is here. So that will be your final position. That will be your final velocity. So we have to distinguish between the position and the displacement. Displacement, remember, you have to connect initial position to the final position. That will be your delta x. Is that clear? But, so on the number line, that means that your position or your final position will be this plus that, right? So it will be, or you say initial position plus delta x. Okay, so it just means that the displacement is the final minus x of r. So sometimes you have tricky problem, but distinguish between the initial position and the origin. That will be your displacement. Is that clear? So you can say final position is initial plus initial speed plus 1/2 a t squared, or you can say displacement equals plus 1/2 a t squared. Is that clear? So it's a lot of, actually, it's really math. Okay, definition of acceleration, the change in speed over the change in time. Final velocity is initial velocity plus at. And then you have this one, which is very convenient. So this equation, we're going to use it a lot. Okay, you have what is missing here that you do have here. Time, very good. So very convenient when you are not given time. Okay, so if you are not given time, you want to use this one. And that comes from conservation of energy, actually. It just says that if there is a change in kinetic energy, that means that someone has applied a force over a distance. That's what is hidden behind. Average velocity by definition is delta x over delta t. Okay? And because the acceleration is constant, it will just be the midpoint. Do you understand that? So it means that if the velocity increases at a constant rate, so you go from here to there, do you understand that it's a constant rate? So the average will be just there, right? So the average velocity in that case will be initial plus final divided by time. It makes sense, right? Just in the middle. Because you take as much time going from here to there that you take from here to there. Agree? Right? So it's like you have 0 in physics to begin with, and the next test you have 10, next test you have 20, and 30, and 40. So what's the average? Do I have enough here? It's going to be 50, okay. So what's the average? It's going to be in the middle, right? It's going to be 25 if you increase at a constant rate. Yes? Makes sense, right? Okay? If there is no acceleration, so you take the same, but a equals 0. So you're going to get that. Okay? So you see, you can think about it. So position, if you are not moving, the position will not change. If you are moving at a constant speed, you're going to get a straight line. And if you have an acceleration every second, you're going to move faster by this amount. So you can think about it. Important for engineers. Okay, let's have fun. So you see, you have your equations here. You should put a delta here. You should put a delta. Forgot the delta. It's because this is anyway. You can put a delta here. That means it's a displacement. The first thing you want to do, but this is done for you, you want to make a drawing. So you see, when you start your stopwatch, it already had an initial velocity. When you stop your stopwatch, it has a final velocity. On the number line, it has initial position, final position, and there is an engine, there is a thrust pushing to the right. So the secret is you need always 3 numbers, not counting the initial position to solve everything. Okay, so you can help each other, talk to each other. Okay. I'm lost. Oh, here. So you have all the equations, you just have to find out which equation you want to use. So you can put a delta here. And to begin with, if it's helping you, you can fill out here. So they want the displacement. So I'm going to put a question mark here. Acceleration is 2. Initial velocity is 6. Time elapsed is 8. And here IDC. I don't care. So I need an equation with delta x, acceleration, initial velocity, and time. Okay, so don't do it. Help each other. So which equation will be appropriate here? 1, right? It's easy, right? So delta x, you see, you connect initial to final. It's going to be initial velocity is 6 times 48, so 8 plus 1/2. So put 0.5, it's easier. 2 times 8 square, right? So, yes. Is that 8? 8 square? So, what do you get? 112. Oh, 112. Okay, so this is 1. When you see that, you say 1, right? So delta x equals 48 plus 64. Okay? So you see, it's not that hard. So we went back to easier stuff. Okay, let's try to do this one. So when they do that, some I think they have a catapult, like they have a sling to make it because otherwise that will be too short. To have enough acceleration, you need enough distance, right? So if you don't have enough distance, they have a system with a catapult, and accelerate very quickly. It's all physics. So do it. More you do in class, less you have to do it at. Why it doesn't charge? Um, I'm going to put a delta x. So here you have 31. Initial velocity is 0, 62, and then 1, 2, 3. Okay, that's enough. Question mark. I don't care. Okay. So which equation to use? So 1, we do not have the time. Well, you could get it, right? You can use this equation to get the time and plug it in. But if you want to get a shortcut, you will use 4, right? So final velocity square equals initial velocity square plus 2 times acceleration and then displacement. That's what I want. For time or displacement? It says displacement. Although you can find the time with equation number 2, plug that in equation number 1. So I'm looking for the displacement, so that's going to be 60. You should put a plus. Okay, what does it mean? It means this, right? You connect initial position to the final position is a vector. Okay? It just happened that the displacement is the final velocity minus the initial velocity, and we can decide that's going to be 0. So you should do the number line, and here position is 0 to begin with. This is plus, you see, plus and minus. Okay? So you see, it's not that hard. I didn't say that. Did I say that? No, I say not here. I'm not using the time. I'm just using this equation to find the displacement. Right? If you want to find the time, you can say acceleration is the final minus initial over time. So you have 31 equals final minus initial over time. And yes, so the time will be 2 seconds. Okay? And once you have the time, you can plug it in here, but it will take more steps. But you can do that. Okay? Yes.
After, like, the second one where it says 62 squared, like, what do you do after that?
So after that, 62 equals 62 delta x. I divide both sides by 62. Okay? It's just because in algebra you are used to have the unknown on the left, but that equation is like having 62 idk equals 62 square. So you divide by 62 on both sides. Okay? I'm isolating the unknown. Right? So I'm solving for delta x. My delta x is like my unknown, my x.
So the answer will be 6.
So the answer will be 62 meters. Oh, by the way, I forgot to show you, talking about relative motion. You see, for example, in astronomy, you have the sun and the Earth is going faster than Mars is going, obviously. So it's like a roundabout. I don't know if you went to England, they are crazy about roundabout. Never understand why. You go and then there's a roundabout, and then you go and there is a roundabout again and again and again. It drives you crazy. Plus, they drive on the other side, right? So very confusing. So anyway, this is like a roundabout. So this is going faster than this one, right? So if you look at the frame of reference of the sun, of course Mars is going go around like this. But if you take the frame of reference of the Earth, right? So first Mars is in front of you, but when you're gonna pass Mars, it's gonna be behind you. So from your perspective, Mars is doing something very weird. So it's called retrograde motion. Okay, so that's why it's a tangent. But it's about relative motion. It always depends on the frame of reference, right? I don't know what I'm doing. I think I wanted to do a problem here, 2.4. Okay, that's what I want to do. That's from your book, by the way. I think it's about a ticket. I have a friend who got a ticket because at the end of the month they need their quota. So you have to be very careful. Okay, so the first thing that you want to do is to draw the situation. Always with a physics problem, don't try to get the equation and plug in like randomly. First, you have your drawing. You make a sketch of the situation. And you don't stare. Nothing will pop out. So do it on your notebook, tablet. Okay, so first thing, so you're going to decide which y is plus, which y is minus. So that's why we learn the methodology. First step. Second step, you make your number line because it's a 1D. And somewhere you take the origin. So that's the speed, the city here. BBC. So t equals 0. Oh, it's easy, right? So we're going to put 0 here, but at t equals 0 is 5 meters away, right? Okay, so that's east, that's west. Okay, initial velocity, it says 15. So if you do that, if you put everything in a sketch, then it's going to be very easy. So that will be your initial position. That's when you start your stopwatch. But the origin is here. I don't know why I make a stopwatch like this. This is a 0 here. Okay, boom, 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 boom. Find its position at t equals 2. So the final position. Okay. So you have different ways to do it, but talk to each other. That's what? No, not yet. Yes. Yes, so equation delta x equals initial velocity plus 1/2 at square. Acceleration is final minus initial over time. V square equals nya 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 nya. Okay. And be careful with the displacement. Here it's a displacement, right? So displacement is, remember, it's a vector from here to there. So help each other. Yeah.
So the last formula, is that initial velocity squared plus, or is that initial velocity times t?
No, the last one is like v squared equals initial square plus 2 times acceleration and delta x. So here they give me the time. So I'm going to use this one. So displacement equals initial velocity is, this is the time elapsed. Acceleration, oh, look at that. Oh, I'm losing point here. I'm supposed to put the acceleration. Acceleration is 4 and 2 square. So how much is that? 38? Do you all agree with that? Is that the answer? Look, what are they asking? That's the displacement. So what will be the final position? 43, right? So the final position minus the initial position equals 38. Okay, so this is 38. This is 38. So the final position will be 43. Yes. Someone ask a question? Okay.
We got it.
Is that clear? So that's why it's very good to lay out the foundation. What exactly is the displacement? You connect the initial position to the final position. But on the number line, when you start your stopwatch, you were already located at 5. So if you want to find the distance to the origin, you need to add 5. Is that clear? So final position, displacement, not the same thing. So if you want to do some math, so that will be the initial vector position, the final vector position, that will be the displacement.
So what is that, 25?
Hmm?
It says 25 meters per second.
Okay, so that question B.
Oh.
That's question B. No, it's because it's small. So question B, where is he? So where is he? So it means location. And you know location. Where is he when his speed is 25 meters per second? Connection. Location.
Okay.
I don't know where I'm gonna hide here. Okay, yeah, I'm gonna hide here. I'm gonna use this one. So where is he? Where is he? So that means find the position when his speed is 25 meters per second. You translate that meaning the final speed is 25 meters per second. And you start your stopwatch here. So that will be, I should have done like this, right? Initial position is 5 and acceleration is 4. Initial velocity is 15, and then you want the final velocity. You have different ways to do it. If you use this, are you doing it? Don't stare, okay? You're doing it. So final velocity is what? 25 squared equals initial velocity is 15 plus 2 times 4 times delta x, which is the displacement, right? So delta x equals what?
Is that the p squared? You're so nice.
8. You can do it a different way, but so what do you get? 50. Do you all agree? 50. But the displacement is 50, but you were already at 5, right? So that means final minus initial equals 50. So x equals final position is 55. Okay, what does it mean? It means that the displacement, okay, so from here to there, it's going to be 50, but you want the position on the number line. You see, this comes from your book. That's why I'm going to tell you every time we meet, do the solved problem. It's important that you use your textbook. Any question? I didn't lose anyone. Yes, yes. Yes.
It's 55.
So for answer B, yes. No. No. Yes. Yes.
First question they were kind of question.
What? This one?
No, first.
What's your question?
Use that the top equation.
Yes, I use this one. But you don't have to, okay? You could have done, you could have say, I don't know. You can do, you could have done, acceleration, for example, is the final minus the initial over the time, for example. So acceleration is 4 equals final is 25 minus 15 over time. Okay, so you can find the time. And once you have the time, then you can do delta x equals initial velocity 15t plus 0.5 a and then t squared. So you could have done it in 2 steps. If you use this equation here, you do it in 1 step. Is that clear? Okay, 10 divided by 4 seconds, and then you plug that into here, and you should get the same answer, except do remember, delta x is the final position minus the initial position. So someone asked me the difference with the other class. In the other class, I don't do that. Okay, you survived? It's just math, okay? It's not much physics here. Okay, so that's just like very important. You make a drawing, you decide which way is plus, which way is minus, you write down, you need 3 numbers to solve everything. You have all your equations on the side and you can solve. Now remember that the equation I gave you not necessarily uses the same notation. So for example, instead of having a delta x, they use delta s for some reason. But of course, the same equations. My point is, when you're going to use this equation sheet for your homework, make sure you understand that the notation is not always the same. Average velocity, instead of being delta x over delta t, they do delta s. Why are they doing that? Because you could be on the x, but you could be on the y. Okay, so that's why they have this different notation. You see here instantaneous velocity, it's going to be the derivative. Acceleration is derivative of the derivative. Okay, and that will be for vectors. And you do have this equation here, right? So make sure you get used to these equation sheets, right? Okay, so now you want to help each other to do the next one, which is this one. So this one is also for the other class, except a little bit tricky here and there. Interesting. So first you want to make a drawing, and they try to trick you because you see kilometers, and it's not consistent here. So first you need to convert, and then they say slow down, and they give you the magnitude of the acceleration. It's the magnitude, but the acceleration needs a direction, right? Because acceleration is a vector. So the acceleration will be left, right? So it's slowing down. So I need to have a negative sign, right? So it's twice tricky. So first thing, you make a drawing. and they want the displacement.
I think they want the velocity, not the displacement.
Oh yeah, thank you. Velocity. They want the final velocity. Yes, yes, you're right. So they want the final velocity. So what do you have? So that will be what? The initial, very good, okay? So the initial velocity, acceleration, they try to trick you because it has to be negative. The magnitude is how much, but I'm missing which way. And then displacement here is 215,000, and you want the final velocity. So I can put 0 here, doesn't matter. So acceleration is -10, so it's gonna slow down. Every second is gonna move slower. So we do not have the time. So we're gonna use our friend v square equals initial square. We have to be very careful with the sign. If you put a positive instead of a negative, you're not going to get the right answer. Oh yes, we know the displacement. Yeah, we know the displacement.
I know. Yeah, I swear lose it.
Okay, so final speed.
Okay.
The second one is this one. Yeah, that's increased. Now it's
2,000.
no, now it's together.
Why would it be done?
Because you need as a social media.
Okay,
Did you guys?
right, do you agree with this?
Yes.
Okay, so 3250 square plus 2 times -10 times 215,000 close the parenthesis. Boom. That's a big number. Then you take the square root. Okay. Up, up, up. And you have this thing. Do you agree? So V equals plus or minus 2, 5, 0, 2.
I did.
My question is, how come you have two values here? What's going to happen if you keep putting those retro rockets? So there is a force to the left pushing down, pushing to the left, right? So you have pushing to the left. So it's going to slow down, slow down, slow down. What's going to happen to it? It's going to stop, right? But the rocket are still pushing to the left. So what's going to happen? It's going to reverse, right? And here it will have exactly the same velocity, but opposite direction. If there is no friction, like only if this force. Isn't that interesting? CO2. I'm going to put a plus, but it's moving this way. Yes.
Just no matter what object or whether it's a car or a spaceship, it's if it's like a negative acceleration, it's going to be the exact same in that specific form.
Yes, except in the car you cannot do that, right? Because you cannot push. You need rockets to do that, right? But yes, so the velocity will be opposite direction. Why? You see the displacement will be the same in both cases. So what does it mean? It means if you throw something in the air, you see you start with 20 meters per second, it's going to slow down, and then you come back here with the same velocity but opposite direction. Right. No, it depends on the situation. It's a good question because sometimes it doesn't make sense. So you need to ask, is that solution is making sense in the real world? So for a spacecraft, yes. For a car, no. Because it doesn't have rockets. So in that case, you say, okay, I keep only that solution.
So you would choose like the power space.
Yes.
Why would the velocity be considered like in negative games? That's the displacement to the right.
So displacement, okay, so that will be the displacement. So one solution will be when it's on its way to stop, then it stop here. But if you keep pushing the retro rocket, it's going to reverse and it will have exactly the same displacement. So it's not that intuitive. So for this, you have the same displacement in both cases, right? And here they try to make a nice drawing. So you have the spacecraft is moving to the right, but then he shoots his retro rocket in the opposite direction. So it's gonna starting from here, slow down, stop, keep shooting those retro rocket and go the other direction. It's hard to understand that because in the real life you don't have car reversing itself, right? Okay, so that's exactly your question here. That situation makes more sense. You throw something in the air, okay, it's gonna slow down, stop, speed up. On the way up, it's gonna have the same direction that it has on the way down. Okay? So let's try to find the kinematic equation that describe this motion. So you have the acceleration, that's the acceleration due to gravity, so 22 miles per hour per second, which is negative 10, let's say negative 10 meters per second per second. So let's say you take the y-axis. Can you find the kinematic equation that will describe this motion? Okay, so acceleration is always down, negative 10. Initial velocity is 20. Forget about this. Initial velocity is 20. Can you write down the kinematics equation that will describe the the position as a function of time, and it will describe the velocity. Okay, so I'm going to take my just the y-axis, so it's still kinematics, right? Okay, so I'm going to make it easier. I'm going to say initial position is 0. And you have the acceleration. So use the equation sheet here, right? You can use your equation sheet. I don't know where. Okay, so displacement equals. So what's the equation? Initial what? Initial velocity, right? So it will be what? Initial velocity is 20 what? T plus 0.5. What's the acceleration? Negative, right? Negative 9.8. And then T squared. Okay, so equation for kinematics, it's delta S equals initial plus nya 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 nya. And that could be delta X or it could be delta Y. So initial condition, initial velocity is 20, initial position is 0, and acceleration is negative 10. Do you agree? Okay. Acceleration is negative 10. Final velocity equals initial velocity minus 10 t. Is that clear?
Yeah.
Okay, so you see, you can predict the location of something that you throw in the air only if there is no air resistance. Okay, and these are examples, and it's already in my Dropbox. So, and let's see. Let's do an easy one. Yes. So I have one fold, I don't know where, somewhere in my Dropbox, but I go over those problems that you find in my slides. I have videos. Yeah, you just have to figure out the number of the slide, because since I'm always updating my slides, it's not going to be exactly the same name, but you will find them. Tutorial, homework, PDF. Oh, it's in there. So I just have to figure out which number of the slide, because I keep adding stuff, removing stuff. Uh, uh, okay, let's do number 2, just to relax, because it's easier. Number 2. So those are the easy one, right? So those problems are easy. So you can do your thing here. Initial velocity is 30, slowing down. So acceleration is minus 3. Time elapsed is 3 seconds. And they want you to find the final velocity. By the way, you have 2 homework for next week, but the second homework you can wait. Just because I want to get over with the kinematics. 2 homework for next week instead of 1. on canvas. So velocity equals, so look at your equation. Can we use this one? Okay, so final velocity is initial 30 plus I did a mistake? No, it's good. So what, how much is that? 21? Oh, you're right, 21. Do you agree? Yeah. Okay, what is the displacement? So you can use this one if you want. Initial velocity is what? 30 times 3 plus 1 half. Acceleration minus 3 square. And we have the pop quiz, so we're gonna stop.
So in that point five, just the one half when we integrate EAT says
What?
that point five, that's like true. Yeah, is that just from integration of EAT?
Yeah, it's so the equation is delta x equals initial time plus it's 1 half at square. And the other one is v equals v0 plus at. So yes, when you integrate, you're gonna get delta x equals v0 t plus a over 2 t squared. And the constant is there. Okay. Okay. Is it open yet? No, right? Okay, so okay. Remember that the acceleration is constant, right? So if you want to find the average velocity and you have the initial and the final, how do you do that? No, because remember, if something increases at a constant rate, how can we find the average velocity? You do final plus initial, enter, divide by 2, because it's going to be the midpoint. Right? I will get back to that because I don't think it's digested yet. You see, if your velocity increases at a constant rate, okay, so it means here you have a line, the average, so here you have the final and here you have the initial, the average will be the midpoint. So it will be here, initial plus final divided by 2. Okay, sometimes they try to trick you with that. So if the initial is 3, the final is 9. So that will be 6, right? The answer is 6 because it's 9 plus 3 divided by 2. Okay, so for next time you can do that. We're almost done because then it's graphing analysis. You can do read your book, okay? And if you need extension, I'm always willing to extend.